Okay, good day guys. In this video, we are going to learn about strength of materials. Today's chapter is strength of materials, but our focus is going to be on stress and strain, right? So without wasting any time guys, let's quickly take a look at our given question, right? This question is from one of the previous question papers, Mechanical Technology, November 2021, grade 12. So let's look at our scenario. We are given that a tensile force of 90 kilonewton is applied to a solid mild steel shaft. Then the resistant area of the shaft is given as 6.17 times 10 to the power minus 3 meters squared. After the force was applied on the shaft, the original length changed by a distance of 0.012 millimeters, right? Therefore, 8.3.1, they want us to calculate the stress in the material in megapascals, right? So let's go ahead and try to solve that question. 8.3.1, right? Stress, the symbol for stress guys is this symbol, right? It's more like an alpha. Stress equal to force over area guys, right? F is force, it can be in kilo newton or newton, therefore area in meters squared, right? Therefore let's go ahead and rewrite our equation. It's force over area, right? Therefore let's look at the scenario. Do we have the force? Yes, we are given the force. The force is 90 kilonewton, right? Over the area of 6.17 multiplied by 10 to the power minus 3, right? And then we get the answer as 90 over 6.17 multiplied by 10 to the power minus 3. We get something like 14,586.71 rounded to the nearest 2, right? Kilo newton per meter squared, right? Kilonewton per meter squared is also 14,586.71 kilo pascals, right? But then remember, they want the answer in what? In megapascals, right? So MPa guys, megapascals equal to kilo pascals divided by 1000, right? So let's see, we have 14,586.71 all divided by 1000. And then we get the answer as 14.58. Sorry, it's 14.59 rounded to the nearest two places. It's mega pascals. Therefore, this will be our answer for stress, guys, right? Then the stress in megapascals is 14.59 MPa. So this will be the answer. So this will be the answer, guys, for 8.3.1. But then I want you guys to look at something. We are given 90 kilonewton, right? But then what if we were given 90 newton instead of kilonewton, right? Or maybe we are given the force in Newton form, right? If you are given the force in the Newton form, guys, the procedure of calculating the stress is still the same. It's F over A, which is force over area, right? But then the different is what is when you have to convert it from pascals to megapascals, because when you use newtons, you're not going to get kilopascals, you're going to get pascals, right? Therefore, let me rewrite the answer here so that I can show you guys how to solve it if you are given it in newtons. 8.3.1, the answer we said the stress equal to 14.59 MPa, right? Therefore, let me create the space. Let me create the space, guys. Okay. So, let me use the black pen. So, the stress equal to F over A, right? And then we've got 90. It's in kilonewton, but then we can convert it to newtons, right? Kilo is 10 to the power 3. Then all divide by area, which is 1.6.17 multiplied by 10 to the power minus 3. And therefore, in this case, we get 90 times 10 to the power 3 divided by 6.17 times 10 to the power minus 3. I'm sorry about that. We get 1,458,609.89, right? In Newton per meter squared. And we know that Newton per meter squared is what? It's pascals. And then kilonewton per meter squared is what? It's kilopascals. Don't confuse the two, guys. .89 and then is going to be pascals. Again, they want the answer in megapascals. Therefore, converting from pascals to megapascals, we say we say megapascals equal to pascals over 1 million. Therefore, let's see, we have 14, 5, 8, 6, 709.89 all divided by 1 million, and then we get divided by 1 million, we get 14.59 rounded to MPa, rounded to the nearest 2. So see, we get the same answer. Our stress is 14.59 megapascals. So it doesn't matter, guys, if you are given the force as kilonewton or newtons, as long as you know the procedure of converting from kilonewton to megapascals. I mean kilopascals to megapascals, or vice versa. So you see, we still get the same answer. So the answer for 8.3.1, guys, is 14.59 megapascals. Okay, so let's go ahead and solve 8.3.2. Okay, so 8.3.2, guys, they want us to determine the diameter of the mild steel shaft in millimeters. All right, in millimeters. So So 8, let me use the black pen. 8.3.2. What is a mild steel shaft, guys? What's the shape of a mild steel shaft? The shape of a mild steel shaft, guys, it's a cylindrical rod shape. So it's a cylinder, right? It's a cylindrical rod shape. Therefore, the area for cylindrical rod shape, guys, is what? It's pi d to the power squared. It's squared over 4. It's pi d squared over 4. Right? So they want us to determine diameter. D is diameter, guys. Therefore, let's make D the subject of the formula. When we make D the subject of the formula, we're going to have A multiplied by 4, right? When we cross multiples, therefore pi d squared. And then we divide by pi. We divide by pi, and then we can see that pi is going to get rid of the pi, right? And we remain with d squared. D squared equal to a multiplied by 4 all over pi. But we are not looking for d squared, we are looking for d. Therefore, we apply square root to get rid of the squared. Therefore, d equal to a multiplied by 4 all over pi. So that's the formula to do it to calculate the diameter of the mild rod shaft. So from here we can easily substitute So when we substitute, we'll say area, which is 6.17 multiplied by 10 to the power minus 3, right? Then multiply by 4 all over pi. And then we punch everything into the calculator. And then when we punch it, square root of 6.17 multiplied by 10 to the power minus 3 multiplied by 4 all over pi, we get 0.0886. It's too many digits, guys, after the decimal point, right? And then millimeters, not millimeters. It's meters, but then they want our answer in millimeters. So moving from meters to millimeters, we do what, guys? We multiply, right? We multiply by 1000. Therefore, our D is going to be 0.08863 multiplied by 1000, and then we get 88.63 meters, rounded to the nearest 2. Therefore, this will be our answer, guys, for 8.3.2. So I'll write it here, guys. D is 88.63 meters. Okay, so that's it for 8.3.2. So let's carry on and solve 8.3.3. Okay, I'm going to erase these, guys. Need some space. Okay. 8.3 they say 8.3.3 they say calculate the original length of the shaft in millimeters if the strain is given as 1.64 times 10 to the power 10 times 10 to the power minus 3. Okay, so 8.3.3. Okay, let me switch my pen to a black pen. They want us to calculate the change in length, guys. Okay, to having the strain, we know that strain, right? Strain, guys, they use the letter E, which is the small e, right? The letter E. In some books, they use this E, right? And then some other books, they use small letter e, right? Reason being that we have e, right, in this chapter, but then it represents the young modulus. It represents young modulus, guys, right? So to clear the confusion, for strain they use small e or this kind of e instead of capital letter E. Okay, so strain is equals to change in length over original length, LO. LO is original length, guys, right? Therefore, to find LO, we have to make it the subject of the formula. So doing cross multiple, we're going to have E multiplied by LO equal to change in length. Therefore, we divide by E, we divide by E, and then E is going to get rid of the E. We remain with the original length this side, which is LO equal to change in length over E. Therefore, from here we can substitute, right? And then change in length is given as 0.012, right? It's in millimeters, guys, right? And then the strain does not have SI unit, guys. I'll explain it to you right away. So we have the strain as 1.64 times 10 to the power minus 3, and then let's put everything into the calculator. 0.012 over 1.64 times 10 to the power minus 3, and we get 7.32. We get 7.32 millimeters. It's rounded to the nearest 2, guys. So this will be the answer for 8.3.3. 8.3.3 LO equal to 7.32 millimeters. So the reason why the strain does not have SI unit, guys, is because if you can check, change in length is in millimeters, right? Or meters, it depends. And then length, which is the original length, will be also in millimeters or meters, right? Therefore, this SI unit, they're going to cancel out, guys. Hence, the strain does not have SI unit. So that's it for this video, guys. I'll see you in the next video. Thank you.